Welcome to Practice 7 for CircuitLab, Electromagnetics and Motors. My name is Mr. Burleson, and you can reach me at geaux15@hotmail.com. So we're going to follow our normal agenda today. And so let's talk about what are north and south poles. We talked about this previously a couple of practices ago. If you break a magnet in two, it forms two magnets, each with a north and south pole. The north and south pole are the same or similar to the positive and negative charges for electric fields. When you break a magnet in half, it forms two other magnets, both with a north and a south pole. The magnetic field flows out in a loop from the north pole around to the south pole and back through the magnet. It's very important that you put the arrows on the field lines to show that. When magnets are near, the lines of force go from north to south pole. A north pole is attracted to a south pole, and a south pole is attracted to a north pole, as shown in the diagram to the right, upper right. However, two north poles or two south poles will actually repulse each other. And you'll notice there's no interaction between the fields of the magnets on the lower right-hand corner. A compass is a navigational instrument by which the north pole of the compass, because remember the arrow on the compass is just a magnet, will always point towards a south pole, a magnetic south pole. And so another common thing is, as you see on the far right here, is that they'll ask you to draw which way the compass would be pointing depending on where you put it, and it will follow the magnetic field lines. That's why it's so important to be able to draw magnetic field lines. And here you can see all the field lines form loops, partially through the magnet, but also outside of the magnet. Earth's magnetic field is why we use compasses for navigation, but keep in mind that the magnetic poles do not exactly line up with the geographic poles, which is the spin axis of the Earth. Okay, so one thing to keep in mind is, and then the other thing to keep in mind is that the geographic North Pole is really near the magnetic South Pole. That's why the North Pole of your compass points north. So there's different types of shapes, and you'll need to draw the magnetic field lines for each of these different types of shapes. But the new thing we want to talk about today is, what about inducing a magnetic field with moving charge, with current? So current going through a wire causes a magnetic field going around it using the right-hand rule. And what we mean by the right-hand rule is that when the current goes in the direction of the thumb on your right hand, the magnetic field line curls around it in the same way that your fingers would curl around it when you close your hand. Okay, and so whenever we talk about a right-hand rule, you find out the direction and you point your thumb in it, and then you, with your hand open, and you close your hand, and it will show how it rotates around. The magnetic field line is shown by the term B, okay, and it's got the equation of permeability, mu, times the current divided by 2 pi r. Okay, so what that means is the further away you are from the current line, the less the magnetic field. And you'll notice that it drops off as 1 over r, not over 1 over r squared. The permeability of free space is the permeability of air or vacuum, and it's equal to 4 pi times 10 to the minus 7 Tesla times meters divided by amps. And so you'll notice that in this case, B would be in Teslas. Now you can also create a magnetic field using a current loop. In other words, if I've got current going around a wire, as shown here, the current will cause a magnetic field that will be concentrated on the inside of the loop. Okay, so this is akin to creating a permanent magnet using just the current. Okay, So what you do in this particular case is that you have your right hand fingers follow the current, and then your thumb will point in the direction of B, or the magnetic flux, and that will be the direction of the magnetic field lines. It'll always be, and so that's where we create a north pole. So the thumb follows the north pole. So in this particular case, you'll notice the electric current goes from the wire on the lower hand straight into the loop, and then goes around counterclockwise, and then comes back out on the upper wire. So in the loop, when I follow it around with my right hand, my thumb points in the direction of the north pole that I've induced. And again, if I want to know what the magnetic flux is, it's B is equal to mu times I divided by 2R. Okay, you notice it doesn't have the 2 pi r, and the reason why it doesn't have the 2 pi r is because that was for the single wire, and you'll have to remember that in that particular case we were forming circles around. The permeability of free space remains 4 pi times 10 to the minus 7 Tesla meters over amps. So what if I take those loops and I keep doubling up those loops? Okay, if I keep doubling up those loops and then tripling the loops and adding in, let's say, a whole bunch of loops, let's say n number of loops, I can create an electromagnet, or it's also called a solenoid. So what happens here is that the more times I wrap I have turns, the more magnetic field I can create. And so if I have twice as many turns, I have twice as much magnetic flux. If I have 4 times as many turns, I have 4 times as much magnetic flux. If I have 100 turns, I have 100 times the magnetic flux. So, and again, we follow the right hand rule. So if you know which way the current is going, okay, then what you will be able to determine is that once you know which way the current is going, you follow the current around just like you did in the loop, and your thumb will point to the north direction. And then that way you can then draw it, and you'll notice that you draw it the same way you draw any type of magnet. Now these can be incredibly powerful magnets. And in this case, B is equal to mu times N, being the number of turns, times current. Okay, so as you can see, I can create a really powerful magnetic field inside. I can very easily change it depending on how much current I put it on. If I turn the current off, then all of a sudden the current drops to 0, and so my magnetic field turns to 0, so I can turn off the magnet. Now, keep in mind, N is the turn density, so it's turns per meter, okay? And the other thing that's really cool is that I can put a different type of core inside all of these loops. If I put like an iron core, that's going to have like 200 times as much magnetism. So if I put multiple loops around an iron core, I can create a really powerful, strong electromagnet. Okay, now if I just have an air core, it will still be a decent electromagnet, but it will be 200 times less magnetic as if I had an iron core. Okay, so just remember, electromagnet is another name for a solenoid. Okay, and it's the number of turns over the length or the turn density. That's really what can dramatically affect the strength of the electromagnetic, or you can change it with a current, or you can change it with a core material. Okay, so a lot of people ask, what does a magnetic field look like? And somebody came up with this particular GIF, which you can look at, and it will show you what it generally looks like. And what you'll notice is that each turn forms circles, but when the circles are put right next to each other, that's how they form the big loops that look a lot like a normal magnetic field from a regular magnet. So if we know that the electric field times the charge is equal to the electric force, okay? And you might remember when we studied Coulomb's law, we were determining the force, and it was always multiplied by the charge in coulombs. Well, if you divide that force divided by the coulombs, you actually get the formula using Coulomb's law for the electric field. So Q times the electric field is equal to the electric force. So it's the force by the electrical force. Now, you can also determine the same for the magnetic force. Okay? And the force of the magnetic field is equal to Q, which is the amount of charge, V cross B. Okay, now V cross B is, what it says is that that's the velocity, V is the velocity, and B is the magnetic flux. Okay, now V cross B is, again, we use the right-hand rule. Okay, so in other words, the direction of the charge flowing crossed with B will be the force that is exerted upon that charge. And so, like, quite often what you'll use is you'll use a magnet to steer a moving charge. And this was used quite often in the old cathode ray tubes, the old TVs, where they would shoot basically an electron, okay, and then they would use powerful electromagnets to then bend the path of the electron so that they can aim the electron very precisely on the screen, and by doing that they could draw the pictures. So what are electric motors? So basically an electric motor is something that takes that magnetic force that is created, remember it's Q, V, cross B, and it turns that into mechanical work. So by providing more current, by providing some current, and these things usually have thousands of turns, and they've got iron cores, they create massive amounts of magnetic energy, which then creates magnetic force, and they spin usually. Okay, so they turn that electrical power into mechanical motion or work. Now, if you want to make it into if you want to use one of these for a generator, usually it works exactly the opposite. Like if I turn a motor, it will actually generate electrical current. Okay, the moving part of a motor is always called the rotor for rotating, and the stationary part is always called the stator for stationary. Now, if you reverse, and this is with DC motors, if you reverse the direction of the current, you'll actually make the motor spin backwards. And so we're going to get more into motors later on, but this is just an introduction. So let's talk about how to draw these field lines and indicate attraction or repulsion. You'll notice that these basically, in these particular cases, I am taking the solenoid or the electromagnet and I'm using it to replace the permanent magnet. So I want you to use your fingers and follow the current, and then with your right hand, and then follow it around, and whichever way your thumb is pointing is the North Pole. So on the far left hand case, the North Pole actually ends up being out the top. So the bottom is the South Pole, so therefore that is repulsed. The magnet below is repulsed because the South Pole and the South Pole repulse each other. Okay, you'll notice the next one, the electromagnet is set exactly the same. So the North Pole is at the top and the South Pole is at the bottom. So the South Pole is right near the North Pole of the horseshoe magnet, and so they are very much attracted to each other. Okay, now in the case in the third case, okay, the current's actually going the opposite direction. So now when I follow it around, the north pole is at the bottom of the solenoid or the electromagnet, and at the top is the south pole. Now, since it's iron, it's going to induce iron to turn into a magnet. So what will end up happening is that the north pole is closest to the iron, so it will induce a south pole in the iron at the very, very top, and they will be attracted. And at the bottom of the iron, a north pole will be induced, and they will be much attracted. Okay. In the final one, on the far right-hand side, I follow the current around the solenoid, and what I'll figure out is that on the left-hand side will be my north pole, and on the right-hand side of the solenoid will be my south pole. Now, of course, it'll be attracted to the iron, so what it will end up doing is it will end up inducing a south pole on the left-hand side of the iron and a north pole on the right-hand side of the iron. So, using the equations in the practice, what was the magnetic field strength for B for a solenoid with the following parameters? 10,000 turns per meter. The current is 0.05 amps, and it's an air core. And so with an air core, you can assume free space usually. Okay. Now, if the magnetic field, if the air core is replaced by an iron core, go back, look at the permeability of iron, which should be one of the things that you should have in your binder, and you multiply it by that, and it will be much stronger. Okay. Now you'll notice in this particular case, we doubled the current. We doubled the current, and that's the only change. I want to see if you can figure out what the changes are to the magnetic field strength, and think and see if that makes sense. So, generally speaking, if you can, I'd like you to find a DC motor. You can find at most hobby stores a 3-volt motor that works really well. Okay, and I want you to look at the voltage across the motor while stopped. I want you to look at the voltage across the motor while it's running and figure out which direction the current is flowing. Because what you're going to find out is that most motors have got some sort of intrinsic resistance to them. Now, if you reverse the polarity of the battery, see if it's changed the voltage, but more importantly, has it changed the direction of the motor and the way the current is flowing? Now, one of my favorite things to do, and we'll do this in the live version later, is that we will wrap a piece of wire around something and create our own solenoid. Okay? And then we will attach that solenoid to a battery, and then we will notice that it will create it will induce a magnetic field. Okay, and then what I usually like to do is I usually like to wrap it around an iron core, usually like a big bolt, and then I compare how strong that magnetic field is with the iron bolt in it and the iron bolt outside. And the iron bolt within it is always a stronger magnet. So, the homework, describe how to make an electric buzzer or bell using a DC power source and draw one. So what this is that it's basically going to be a bell, okay, that when the circuit is completed, it forms an electromagnet which strikes the bell. And then, however it strikes the bell is going to basically turn off the electromagnet, so then the magnet stops. It falls back in, backwards, and then that completes the circuit, turns on the electromagnet, and causes it to hit it again. This is a very, very common practical and a very, very common question on tests. Also, describe how to make a telegraph using a DC power source and draw one. Again, both of these you can look up on Google and Wikipedia. There's lots of different approaches. Know a few of them. And then I'd like you to do level 1 magnetism, level 4 combination, and level 5 combination. Thank you so much, and have a great day.